Okay, I will share my screen. Okay, now let me turn on. Last week we started with three-position synthesis of a moving plane. We said whatever we have discussed for 2 positions of a moving plane is applicable for 3 positions, because I can always neglect one of the positions and consider 2 of the positions. In that case, that means I'm going to have 3 poles. Very simply, if I want to design it, I can, on the moving plane, I can select any 2 points, A, B, whatever you call it. I can draw the perpendicular bisector to 2 pairs of homologous points, A1, B1, A2, B2, or A1, A2, A1, A3, or A2, A3. There are 3 perpendicular bisectors that you can draw through the homologous points. I'll pick any 2 of them. The point of intersection is going to give me the center point, and A will be the circle point. Of course, that means since I can select A in infinitely many ways, B in infinitely many ways, for selecting A, I have 2 parameters. For selecting B, I have 2 parameters. Now this means I have 4 parameters that I'm free to select. Unlike the 2-position synthesis, we had 6 parameters. Now we have 4 parameters, 2 for each circle point and center point. Now, this is not enough. So we determine the pole triangle. The pole triangle is the triangle formed by the poles taken to, if I take 2 positions at a time, I have 3 poles, P12, P13, and P23. This is the pole triangle. P12 is common for position 1 and 2. P13 is common for position 1 and 3. P23 is common for positions 2 and 3. If the moving plane, when the moving plane moves back to position 1, P23 is not going to be over there. It is going to be rotated about P12 by an angle minus phi12 to come to this, or it will be rotated about P13 by an angle minus phi13. So it will move to some other location. If I rotate P23, every point, if I select a point A3 over here, I can determine, C3, let me call it. I can determine C1 by rotating C3 about P13 by an angle minus phi13. Okay? If I select a point C1 over here, I can determine C3 by rotating C1, P13, about P13 by an angle phi13. I do the reverse for if I select C3. So that means I can determine P23 in position 1, either by rotating P23, since it is common point for positions 2 and 3, I can either rotate P23 about P12 by an angle minus phi12. I can, or I can rotate P23 about P13 by an angle minus phi13. Now, the internal angles of the triangle, if I label the size by the common subscript P12, P23 as 2, P12, P13 as 1, the angles, the internal the angles formed from that you on after by this triangle from side 1 to side 2 is equal to half of the angular rotation from position 1 to position 2, phi12 over 2. From side 2 to side 3, it is phi 2, 3 over 2. From side 1 to side 3, it is phi 1, 3 over 2. Angles are always directed angles. Okay? Angles are always directed angles. And one other thing is, the sum phi 1, 2 plus phi 2, 3 has to be equal to phi 1, 3 over phi 1, 3. Because if I rotate the rigid body first by an angle phi 1, 2, and then by an angle phi 2, 3, I come to position 3. So phi 1, 3 is going to be equal to either phi 1, 2 plus phi 2, 3, or by a difference of 2 pi. The internal angles of a triangle add up to 180 degrees. That's also true in this case. Phi 1, 2 over 2 plus phi 2, 3 over 2 plus phi 3, 1, 3 over 2 will be either equal to pi or 0, according to depending on the direction you select. Now, the internal angles of the pole triangle for 3 finite positions of the moving plane are equal to the halves of the corresponding angles of rotation measured as directed angles. Okay? The pole triangle completely defines the motion for 3 positions. Okay? The motion between 3 positions is completely defined by the pole triangle. The reason why we are using pole triangle is I can select any 2 points A, B on the moving body. And you can select any 2 points on this body. They may look different. Whenever you select these 2 points A, B, they may look different. But no matter who selects those points, which points you select, you end up, if the motion is, if these 3 positions are the same, you always end up with the same pole triangle. Okay? Although these points can be different, the pole triangle will be invariant. It will not change depending on the points that you select. Now, the image pole triangle, let me repeat, we can obtain by rotating P23 about P12 by an angle phi 12, minus phi 12, sorry. You can determine P231 by rotating P23 about P13 by an angle minus phi 13. Okay? That is P231. When the motion is inverted, meaning if I keep the moving body fixed, release the fixed body while keeping the relative positions the same for these 3 positions, what is the pole triangle is now, for the inverse motion, will be the inverse pole triangle in position 1. If I keep my moving body fixed in position 1, okay? This will be the inverse pole triangle. P12, P13, P231 is the inverse pole triangle in position 1. Okay? If you keep the rigid body fixed in position 2 and determine the relative positions of the fixed plane, then it will be the pole triangle P12, P132, P23. P132 will be the, you will have to rotate, take the image of 13. Okay, you have to rotate P13 about P12 by an angle minus phi 12. You have to rotate P13 about P23 by an angle minus phi 23 to come up with P132. Okay, so, but simpler way is, if you want to determine the image pole triangle P13, 2, you simply take the image of P13 with respect to this side too. You drop a perpendicular, okay? Make that equal, those equal. You determine P2, 3, 2. It's that simple. Let me where is it? Oh, sorry. Turn on a Geogebra sheet. I have already prepared this because I don't want to spend too much time on time. I have 3 positions: A1, B1, A2, B2, A3, B3, as you see over here. I have obtained this pole triangle, these poles, by drawing the perpendicular bisectors to A1, A3, B1, B3. I determined P1, 3. By drawing a perpendicular bisector, by determining the intersection of the perpendicular bisectors to A1, A2, B1, B2, I determined P1, 2. Labeled the size S1, S2, S3. The reason is I cannot label these size as 1, 2, 3. So I used S. In GeoGebra, I cannot label the side as 1. So it has to be literal. So I said, I called it S1, S2, S3, side 1, side 2, side 3. Now I have this whole triangle. I have the 3 positions, but these 3 positions are not important. I could have selected some other point. Now, I'm going to select a point, rename it as C-1 over here. I can select it anywhere you like on the moving plane in position 1. This is my moving plane. It is of infinite length. I can select C1 over here, over here, over here, I don't care. Now, I can determine C2 and C3, as we discussed last time, and it was in your homework, by rotating C1, P1, 2, by rotating this line about P1, 2 by an angle phi 1, 2. Can I measure phi 1, 2? Yes. Half of it is this angle. For example, let me show that. This angle from here to here is alpha, and that is 26.47 degrees. The rotation will be twice this, from point 1 to point 2. So I will say, if you want, I will rotate C1, P1, 2 by an angle 2 times alt alpha. Oh, degrees, radians, sorry. You see? Oh. I think I'll erase it and redo it. I think I'll delete this. That's C1, right? Okay. 26.47 degrees. So I will rotate, or let me use this rotation. I will rotate C1 about P12 by an angle, counterclockwise direction, 2 times alt alpha. That's a counterclockwise rotation.
Hocam degree yine kaldı.
Oh, thank you. Yes, here. You can see that, okay? I will hide this. This is going to be, rename it as C2. I will hide this. I can as well determine that point C2 as follows. I will take the image, reflect, it says, take the image of C1 about side 1. Okay? I come over here, this point. This point I will call ground point or base point, C-G. In the notes, I have also used C123. That's also possible. That's also common. But now I will use C-G. That is the ground point, base point. The reason I'm using G is it's much simpler to type G rather than typing 1, 2, 3. That's why. If you want, I can change to 1, 2, 3. Okay, very easily rename it as C-1, -2, -3. So the previous case, typing C-G is much simpler. That's why I'm using it. Okay, I'll keep C1, 2, 3 now. Now this ground point or base point, I can reflect, I can take the image of this base point with respect to side 2. I can take the image of this base point with respect to side 3. This point is going to be C2. This point I will relabel as C3. Okay? Now please look. I have hidden C2. Now I'm turning it on. What do you see? C2 and A are exactly at the same position. So I will delete this C2, delete it. I'll call this point, rename it as C-2. The reason, let us explain this. Now, please look at this these two triangles. See this intersection of this line with the side 1, it is the image. So this length is equal to this length. So the triangles, let me select a point over here. C1A is equal to AC123 and C1P12 is equal to C123P12. AP12 is common. So these two triangles are exactly equal. That means these two angles are exactly equal. The same thing applies for these two triangles. C2, P12, and let me determine the intersection point. These two triangles are equal. So these two angles are equal. That means the total angle C1, P12, C2 is going to be equal to twice the angle P13, P12, P23. Can everybody see that? Any questions? Oh. I will delete these because I don't want to complicate the figure. I will delete these also. Oh, let me keep that. But I have to delete, hide the labels, otherwise I'll get into trouble. There will be too many numbers or letters on the board. Okay, now let me determine the center point. Sorry, not that. 3 points, C1, C2, and C3. The center, midpoint or center, this is going to be C0. Okay? Now, we have determined C0 by drawing the circle through 3 points. Please keep this in mind, this construction in mind. I'll keep this file, save as 3 positions on, solved in class. Okay? Let me turn back to PowerPoint. This is what we have done till now. We have selected a point C1, determined C1, 2, 3, the base point, determined C2, C3, just by taking the image of C1, 2, 3 with respect to side 2 and side 3. And then we determine C0. Now, the thing is this. We know P13, P12, P23 is equal to 512 over 2. C0 is on the perpendicular bisector to C1, C2. And this perpendicular bisector passes to P12. So any point on the perpendicular bisector will bisect the angle C1, P12, C2. C1, P12, C2 is 512. So C1, P12, C0 is going to be equal to 512 over 2. Any questions on this, please? It's very simple because C0 is on the perpendicular bisector. As the name implies, perpendicular bisector bisects this angle. I don't care, it need not be P12, by the way. Any point on this perpendicular bisector, let me say I have selected a point Q over here. Q, C1, Q, C2 will be bisected by this perpendicular bisector. Okay? Now, let us consider the following. C0, P12, P23. The angle the line C0, P12 makes with respect to side 2 is equal to C0, P12, C2 minus P23, P12, C2. Can everybody see that? C0, P12, P23 is equal to C0, P12, C2 minus P23, P12, C2. Now, C0, P12, C2 is 1/2 512. P23, P12, C2, P23, P12, C2 is equal to C123, P12, P23. Why? Because we showed that since this is the image, C123 and C2 are the images with respect to side 2, these two angles are the same, correct? In terms of direction, C123, P12, P23 is equal to P23, P12, C2. So I can write C0, P12, P23 is equal to P13, P12, P23, which is also equal to 512 over 2, minus C123, P12, P23. P12, P12, P23, minus C123, P12, P23. But that is equal to P13, P12, C123. The angle made at P12 by C0 with respect to side 2 is equal and opposite to the angle made by the base point with respect to P12 with respect to side 1. Okay? Now I can generalize this. These two angles are the same. This angle and this angle is the same. So I can generalize this. I can repeat the same process. I can say the same thing if I consider P13 or P23. These angles will be also the same. C0, P12, P23. The angle made by C0, P12 with respect to side 2 or side 1, it doesn't matter, will be equal and opposite to the angle made with C123, P12 with respect to side 1 or side 2. Let me repeat, I have reversed the order. What this angle is equal to this angle, okay? Or vice versa, if I consider the C0, P12, P23, C123, P12, P13 will be equal and opposite, okay? And I can repeat, for example, C0, P13, P23 will be equal and opposite to the angle C123, P13, P12. Okay? Okay. I can repeat this. Now, this we state as a theorem. The angle formed at a pole by one adjacent side of the pole triangle and a line drawn from the ground point or base point or the center point is equal and opposite to the angle formed by the other adjacent side and a line drawn to the center point or the ground point. Those two are equal. Now, how can I make use of this? Remember, in certain problems, we are free to select the circle point, and then we determine the center point. In case of three-position synthesis, once you fix the circle point, the center point is fixed. In certain problems, that is not good because center point has to be at a specific location. Now, using this concept, I can select C0, determine the base point using this theorem, or what we have proven, determine the base point, and then reflect it with respect to side 1, side 2, and side 3 to determine the circle point. Okay? Now I'm free to select C0 in infinitely many ways. I have two parameters. And then I can determine the circle point for that center point. Okay? That is the idea. Now let me go back to GeoGebra again. Shall I go to this one? Okay, I'll do this. No, I don't think I will be able to show it on. So what I will do is this. I can do this, show it with this file, but I will do something different, solve a different problem. Where is it? Okay. I have these three positions. Oh. Oh. Let me, sorry. I have these three positions. I'm going to select A1 over here, as I showed. I can, move it. This is point A1 on the moving plane. Okay, and I want to select B0 on the fixed plane over here. I want to determine the center point A0, and I want to determine the circle point B0. Any questions? For these three positions, this is the pole triangle. I'm not going to repeat, as draw the perpendicular bisectors. It's that simple. Now I want to determine A0 and B1. To determine, first let me start with A1. I reflect A1 with respect to side 1. This point is going to be, rename it as, this time I will rename it as A-G. If you want, you can label it as A123 or A-G. This is my ground point. I will connect this ground point with P12 and P13. I can connect it to P23, but it will be more, this figure will take a bad shape. So the lines will be overcrossing. So that's why I selected these 2 points. Now, according to the theorem, the angle made by AG P12 with respect to side 1 must be equal and opposite to the angle made by A0 with respect to side 2. Can everybody see that? So what I do is, I will first measure the angle AG P12 makes with respect to side 1. It is alpha 122.79 degrees. The angle made by C0 has to be equal and opposite. So C0 must be on the line, angle with a given size. P23, P12, this time it is alt alpha in counterclockwise direction. Now, please look. This angle is equal to this angle. AG P12, P13 is equal to and opposite to P23, P12, this line, A. I'll hide A. I'm not going to use it. Is that agreed? C0 must be on this line. A0, sorry, A0 must be on this line. I will repeat the process. The angle made by AG P13 with respect to, sorry, cancel. I'm sorry. I'll measure the angle. The angle made by AG P13 with respect to side 1, notice it takes the counterclockwise angle, gamma, must be equal and opposite to the angle made by C0 with respect to side 3, because at this point, side 1 and side 3. So I measure P23, P12, and that angle is alt G, O, in counterclockwise direction. Please note this. Here it is. Okay? I'll hide this. Now we have, I'll hide these angles. Oh, sorry, not that. I'll hide these angles. Oh, sorry. So that, because otherwise the figure gets more and more complicated to view, okay? The point of intersection of these two lines is going to give me, rename it as A-0. Okay? Now, let me hide this line. Hide this line. That is A0. I'll also hide A0. Let me determine A1. I have AG. Take the image of AG with respect to side 2 and 3. This is going to be A2. I'm doing the same thing twice. Take the image of AG with respect to side 3. Rename it as A-3. I will determine the circle passing through A1, A2, A3, and then determine the center of that circle. That's C. Now let me turn on A0 again. Can I see that? I have determined C. A0 and C exactly coincide. So that's a good procedure. I will delete this so that I have A0. Okay? Now, let us see B0. By the way, I can, okay, let me repeat and then I'll show you something else. I will let me hide these lines because I have completed determining A0. Okay. Let me determine B1. I will repeat the same process. I will join B1, B0 with P12. and with P13. I don't use those labels, so I'll erase. The angle made first by B0, P13, P12, epsilon is that angle, must be equal and opposite to the angle made by the base point, BG, with respect to, with respect to side 2. I don't know how to type epsilon. View keyboard. Epsilon is where? Oh, can you see? Oh, right here. No. Yes. Is that agreed? Where is it? Should be. Did I do it correctly or not? No, I haven't done it. Epsilon, no. Okay, I'll repeat it. Measure this angle. P23, P12. Yes, here. BG must be on this line. Similarly, B0, P12, P23 is angle eta. The angle made by the other side, P23, P12. If I'm not mistaken, it is Alt H. No. No. No, I don't know it. So. Eta. You must always check the results to see that the angles are the same, okay? P13, P12, B0, this angle must be equal to P23, P12, this line in opposite direction, notice. Check it. Now, corresponding to B0, this point is going to be the intersection of those two lines is going to give me B sub G. Base point. Let me hide these. I'm not erasing them. I can always turn them on. But if I keep them, okay. If I take the image of BG with respect to side 1, it's going to give me Yes, rename it as B-1. Okay? Any questions, please? A0, A1, B1, B0 will be a possible four-bar to move the rigid body in between these three positions. Of course, you have to check. Nobody gives you any guarantee on that. But let me show you something else. I said I can determine B1 as a center point for B0 in the inverse motion. Let me do that. I will determine P231 by taking the image of P23 with respect to side 1. P-2-3, 1. That's P231. The image pole triangle is going to be this. Let me change this color. No, I'll take it blue. In fact, like this. Okay. Oh, I don't change it. Okay. That's the image pole triangle. P231, P12, P13. If this is B0, now side 1, P13, P12 is the same. This side rename it as S prime 3. Can anyone see that? S prime 3. That is the side 3 for the image pole. Rename it as S prime 2. Side 2 for the image pole triangle. Now, I can use this image pole triangle as if it is the pole triangle with B0 as the circle point. I will take the image of B0 with respect to side 1. This point, I will rename it as B-0-G. That's the ground point for B0. If I take the image of B0-G with respect to side 2, this point will be B-0-1. Sorry, 2. I'm sorry. That's B0 is B01. So this is 2. I have taken the image with respect to side 2. If I take the image of B0G with respect to side 3, this point will be B-03. Okay? Did I do something wrong? No. B0. I have taken the image of B0 with respect to site 1, BG. It's not going to be B1. I have to determine the, yes. Draw the circle B0, B02, and B03. Can everyone see that? Where is the center of this circle? The center point for the inverse motion is going to be exactly the same point. Is that good? Can everyone see that? This is this is the point. B1 and that point E is the same. So in the second case, I have simply inverted the motion and performed determined B1 as the center point for B0. In the previous case, I have determined B1 using the theorem that the B0, the angle formed by, the center point with respect to any side is equal and opposite to the angle formed by the ground point with the other side. Okay? Now, in this case, I have simply inverted the motion and determined B1. Okay? I have inverted the motion. Either way is, you see, depending on the application, depending on the problem case, you can use different forms of it. Okay? You can use solve the problem in different ways. This is what I wanted to show. Now, with this, we are able to select B0 in infinitely many ways and determine A0, A1, B1, or select the A1 in infinitely many ways and determine A0. Now, I think you can see that. You can select different points A1 and determine A0. Now, over here, let me, I can select B0 in infinitely many ways and determine B1. By the way, I can hide all these. If I want to design a 4-bar, I will hide all these.
Hocam, before hiding, can I ask a question?
Of course.
I couldn't really understand what do you mean by inversion of motion here?
What I mean by inverting the motion is, you see, I have a reference frame. I have a fixed frame over here. I'm keeping that fixed frame, and in the original motion, I'm keeping that fixed frame fixed, and I'm looking at the motion C1, D1, C2, D2, C3, D3. Okay? Now, in the inverse motion, I am keeping C1, D1 at C1, D1. And now I'm moving the fixed body relative to that C1, D1, while keeping the relative positions the same. Meaning, I have to move C2, D2 back to C1, D1. I shouldn't observe the motion of CD, okay? But keep the relative motion the same, relative positions the same. This is very important, okay? I am inverting the motion, meaning I'm sitting on the moving frame, and I'm looking at the fixed frame. If I'm sitting on the fixed frame and looking at the fixed frame, if I'm sitting on the moving frame and looking at the fixed frame, when I go to C2, D2, what will I see? Okay?
Do we also do that for C3, D3?
Of course. So
Okay.
there will be 3 different positions for the fixed frame in the inverse motion. Am I right?
Yes, but
Is it agree?
I couldn't imagine, Hocam, actually.
Okay. Let me say this. Take a 4-bar. If you take a 4-bar, consider a 4-bar, originally you are fixing A0, B0, and you are looking at AB. Am I right? AB is moving, that link, coupler link is moving, and A0 is fixed, and you are observing the motion of the coupler with respect to the fixed link. Now, fix the coupler, release the fixed link. What are you going to see? That's the inverse motion.
Okay.
Do you agree?
I was trying to link this with the triangles, but I think I understand now.
Okay, now in the inverse motion, let me say this. If I C1, D1, when moved to C2, D2, is going to rotate about P12 by an angle phi12. For the inverse motion, if I have, let me say, take 2 points, let me consider 2 points like over here like this. Okay, let us say this is our fixed frame. This is our fixed frame. When moved from C1, D1 to C2, D2, the inverse motion will be, I will move C2, D2 back to C1, D1. In order to do that, I will be rotating C2, D2 about P12 by an angle minus phi12, correct? Now, when I do it, FG will, since this is a fixed frame, if I'm going to keep the relative positions the same, FG is going to rotate about P12 by an angle minus phi12. Let us do that. Let me rotate this body. I know the angular rotation 50 degrees, but this time minus 50 degrees. Okay? And the other, let me rotate this FG with respect to the side frame, with third position, inverse motion. It will be a rotation of FG with respect to P13 by minus 90 degrees. Where is that? Somebody sitting on CD will see the motion of the fixed frame as if it is, I'm sitting on CD in the first position, and I will be saying this is the first position of FG, the fixed frame. This is the second position, and this is the third position. Okay?
Okay.
These are the 3 positions of the fixed frame relative to the moving frame. If I determine the poles, let me determine the pole. Oh, sorry. I'll show you P231, okay? P23 for this inverse motion, this point That's the perpendicular, those are the perpendicular bisectors. What do you see? From the second to third position, it is P231 for the inverse motion. Is it agreed?
Yes, I now get it. Thank you.
But let us see whether P13 is the same. I'll show only P13. If I take the perpendicular bisector to these 2 points, as you can see, P13 is the same. Okay, for the inverse motion. I think I'll erase these lines because otherwise it will be too complicated for you to understand. Because I'll be saving this.
Thank you hocam.
Rica ederim çocuklar, lütfen soru sorun. Anlamadığınız bir şey varsa lütfen sorun. Okay, I think I'll give a 10-minute break. Any questions? If you have any questions, please ask. I'll give 10-minute break. And I'll save this file. And I post both the original and the final file together, okay? So that you can see.
Hocam sesiniz gelmiyor. Hocam sesiniz gelmiyor.
Saat için değil mi? Hı hı.
Hocam sesiniz gelmiyor galiba.
One second, please. Alo? Peki, tamam. Hemen şey diyorum. Hemen şey. Tamam, tamam. I think, I'm sorry, you haven't heard my voice. Now I think it's okay. Is that great? If there's any question, please send me a message. I think it's okay. Now, I usually prefer, let me repeat, analytical methods in more complex cases because it's much more, sturdy, let me say. But you will need both of them. And sometimes you use both to check your result. You do it twice. Once in analytical method and then in geometrical method, and you check the two. If there's any inconsistency, that means you have a mistake. You see, usually you ask, what is the solution? What is the result? In engineering, if somebody knows the result, they will not ask you. Okay? You are going to, in your lifetime, as an engineer, you are going to solve problems whose result nobody knows. So you have to sign it. You have to tell, okay, do this. Now, in that case, you have to make sure that what you are doing is correct. So what you have to do is check your result. Do it twice, okay? And usually I do it twice, once in analytical method and then in geometrical method. And I compare the two results because I have to make sure that my result is correct. How can I, because nobody knows the result. It is not an exam question that you have in your courses. In lifetime, as an engineer, you have to solve problems whose solution nobody knows. Okay? So that's the usual thing. Now, in case of analytical methods, consider a rigid body. I have a fixed reference frame, O, X, Y. I have a moving reference frame, O prime, X, Y. In the first position, it is at O1 prime. It is in the jet making an angle phi 1 at a distance A1. This A1 is complex number. Phi 1. This is the moving frame in position 1. In position J, J can be 2, 3, 4, whatever you call it. It is at J's position like this, making an angle phi J, OJ prime. Okay? Now, let me assume I have a circle point A1 or B1. Okay, I know the circle points, and I know the center point A0, B0. Whenever I have determined A0, B0 and A1, B1, these will be rigid bodies. A0 will A1, B1, A1, A0 will be rotated about A0 by an angle beta J, whose value I don't know. Over here, this will be a rigid body. And this vector, A1 O prime, will be moved to this location, AJ OJ prime. Since this is also a rigid body, this distance is going to remain the same. Correct? Now, this vector, A0, A1, if I call it W, it has a certain magnitude and a certain angle, which I don't know. And then A1, O1 prime, let me call it Z vector. Okay? These two are, the link lengths are constant. This length does not change. Or A0, A1 does not change when you move to A0, AJ. But it only rotates. The rotation operator in complex numbers is whenever you have a complex number, if you multiply it by e to I beta j, you rotate that vector w by an angle beta j. This z vector, the vector, and whenever it has moved to position j, it will be rotated by an angle alpha j that is equal to the angular rotation of the rigid body. Alpha j will be equal to phi j minus phi 1 because the whole rigid body rotates the same amount. Okay? The whole rigid body rotates by the same amount. So alpha j will be equal to phi j minus phi 1. The angular position of the moving body at j's position minus the angular position of the rigid body in the first position. Alpha j is phi j minus phi 1. This point, O1 prime, will be displaced by to OJ prime. That distance, I will call delta j, is equal to A1, AJ minus A1. A1 is this length minus A1 plus AJ. AJ minus A1. Those are the position vectors of the origin of the moving coordinate frame with respect to any reference frame you select. Notice I can select this reference frame anywhere I like. It doesn't make any difference. Now I have a vector loop formed. A0, AJ, OJ, O1 prime, A1, A0. This is a vector loop. A0, AJ it should be, AJ, OJ prime, OJ prime, O1 prime, O1 prime, A1, A1, A0. I'll correct this, AJ should be. Now this vector is, let me repeat, W e to I beta j. Whatever the length A0, AJ is, that is equal to the length A0, A1. Correct? Only the angular position has changed. Angle has changed. Now that vector is W e to I beta j plus Z e to I alpha j minus delta j minus Z minus W must add up to 0. Let me repeat. W e to I beta j, W vector rotated by e to I beta j, by an angle beta j, Z e to I alpha j, Z vector rotated by an angle alpha j equal to phi j minus phi 1, minus delta j, delta j is equal to AJ minus A1, minus Z minus W must be equal to 0. I will combine terms, right? W e to I beta j minus 1, these two terms, plus Z e to I alpha j minus 1 is equal to delta j. This is known as basic form or standard form of dyad equation. Two links, A0, AB, A0, A, O prime. That is called a dyad. Two links connected to each other by a revolute joint. A0, A1, AO is a dyad. This is the basic form of a dyad equation. I can write the same equation for B0, B1, O1 prime. Okay, if using the same loop will be formed. So this is the relation that I can use for the other dyad. Okay, same thing, same equation. Can everybody see that, please? If I call this W, this Z, of course beta will be different, alpha will be the same, but beta will be different. Because these two cracks will be rotated by two different amounts. Now, if I have two positions of a moving frame, I can write that dyad equation only once, because relative to J will be equal to 2 only, 2 positions. That equation will be W e to I beta 2 minus 1 plus Z e to I alpha 2 minus 1 is equal to delta 2. Now, for two positions of a moving plane, we are given the two positions. A1, A2 will be given, phi1, phi2 will be given, because those are the positions of the two frames, from which I can determine delta 2 and alpha 2. So in this dyad equation, I know alpha 2 and delta 2. What are the unknowns? W is an unknown, Z is an unknown, and beta 2 is an unknown. In two vectors and one scalar unknown, that adds up to 5 scalar terms, right? W, if you consider a vector in plane, it has 2 components. So it adds up to 5 scalars, unknowns. I have one complex equation. This is a complex equation. It means 2 scalar equations. If I write the real and imaginary parts, it will be 2 equations. I have 5 scalar unknowns, 2 equations. That means I have 3 free parameters. That's what we had for 2 positions of a moving frame. Remember, we were able to select A, B infinitely many ways. Selection of A requires 2 parameters, right? And then we were able to select A0 on the perpendicular bisector. It required 1 parameter, 3 parameters. Now it is the same thing. If you are given a circle point, minus Z is defined. If you are given a circle point, minus Z is defined. This length is defined. Correct? If that is defined, you can solve for W. If minus Z is defined, and then you have to select beta 2 angle. If you select minus Z, and arbitrarily select beta 2, you can determine W, from which you can determine the center point. Correct? Using 3 parameters, you can determine, select circle point, select beta 2, determine A0. Or if you are given the center point, that will mean you will be given O1 prime A0 minus R1, or let me call it R. R is equal to minus R1. In that case, I will select center point this time, and the angle beta 2, again, to determine minus Z. Minus Z is the location of the circle point. Meaning, either I will have a circle point defined and angle beta 2 to determine W, from which I will solve this dyad. Whenever you solve 2 dyads, you will end up with a 4-bar. Correct? So for each dyad, I will solve this equation once. Either circle point can be defined or center point can be defined. If you define circle point and angle beta 2, you solve this equation. If you are given center point, R is equal to minus R1, and beta 2 is given, use this equation. Simply, I have written W is equal to minus Z minus R, substitute into this equation, and solve. minus z is equal. Minus z is the location of the center point, circle point. Minus z is equal to, in terms of Rm beta 2 is given by this equation. So specify 3 parameters, determine the other 2 parameters, which is the coordinates of one complex number, 2 unknowns. Any questions for 2 positions? Now, for 3 positions of a moving plane, I will be given A1, A2, A3, and phi1, phi2, phi3. Correct? From which I will be able to determine delta 2, delta 3, alpha 2, alpha 3. Agreed? Now I can write 2 equations for position 2 and for position 3. W e to I beta 2 minus 1 plus C e to I alpha 2 minus 1 is equal to delta 2. W e to I beta 3 minus 1 plus C e to I alpha 3 minus 1 is equal to delta 3. Again, let us check what is known and what is unknown and how many parameters we have. This is 2 complex equations. We have 2 complex equations. In these 2 complex equations, we are given alpha 2, alpha 3, delta 2, delta 3. Whenever you have specified 3 positions, those are fixed. You want to satisfy those values. In that case, in this equation, we have W, Z as 2 vectors or 2 complex numbers. And then we have beta 2, beta 3, 2 angles, crank angles, beta 2, beta 3. WZ, 4 unknowns, beta 2, beta 3, 2 more, 6 unknowns. I have 4 scalar equations, 2 complex equations correspond to 4 scalar equations. 6 unknowns, 4 scalar equations. If I am given 2 parameters, values of 2 parameters, I should be able to solve these 2 equations for the other remaining parameters. Correct? Can everyone see that? For each dyad, this is one dyad, A0, O is one dyad, B0, B, O is the other dyad. I should be able to solve. I have to define 2 parameters. Now, the first simple thing to do is, if you look at these 2 equations, if I specify, can everybody see that? I have 2 free parameters that I can select. In geometrical method, as you know, we have to either select the circle point or center point. This time, when you select, for example, circle point, minus Z is given. Z value is given. In that case, you have to determine, solve for W, beta 2 and beta 3, 4 parameters. In case of R is given, A0 is given, center point is given. Again, you will need you have to solve these 2 equations for 4 parameters. But there's another way, a very simple thing. If I am given the crank angles, beta 2, beta 3, you see what happens is, if beta 2, beta 3 is given, we have 2 complex equations in 2 complex unknowns, W and Z. Can everyone see that? And one beautiful thing is, these 2 complex equations in terms of W and Z are linearly related. They are linear equations. We engineers love linear equations because it's simple. Because we know when the solution exists, what kind of a solution we have. We can solve everything. It is the nonlinear equations that creates problem. It is the nonlinear equations that we have to tackle. In this case, if we are given beta 2 and beta 3, the Planck angles, notice, I have two complex equations in two complex unknowns, W and Z. Using linear algebra, W will be equal to determinant of W, coefficient of W replaced by delta 2, delta 3, and then the coefficient of a matrix, determinant of the coefficient matrix. This ratio is going to give me W. Replace the coefficients of Z by delta 2, delta 3. That will give you Z. I can solve these two equations. This is known as, basic form, given Planck angle specification, we call it. Whenever you have a Planck angle specification, all you have to do is solve for W from this equation, solve for Z from this equation. They are complex equations, but nowadays solution of a complex equation is no problem. You can, if you use MATLAB, MathCAD, whatever you have, Excel, these things can be solved very easily. Okay? I have two complex equations to be solved, W and Z. Now, I'll discuss the solution in a minute, but let us discuss another thing. What if I specify the center point? When I specify the center point, I will be defining this vector R. R is O1 prime A0. It is the location of A0 with respect to the first position of the, with respect to a fixed frame whose origin is at the first position, okay? This is the fixed frame whose origin, XY frame, is the fixed frame, whose the vectors I have measured with respect to this XY frame, capital X, capital Y frame, fixed frame. R is the position of A0 with respect to this frame, okay? Not measured with respect to the moving frame. R1, W plus Z is equal to minus R. And that I will call R1. Now I will write W e to I beta 2 plus Z e to I alpha 2 is equal to W, it will be minus W minus Z plus delta 2. Let me show that. Okay. Oh. W e to I beta 2 plus Z e to I alpha 2 is equal to W plus Z plus delta 2. Correct? W plus Z is equal to R1. Okay? So W e to I beta 3 plus Z e to I alpha 3 is equal to R1 plus delta 3. W e to I beta 2 plus Z e to alpha 2 is equal to R1 plus delta 2. Correct? If R is given, R1 is known, delta 2 is known, delta 3 is known, alpha 2 is known, alpha 3 is known. It is given three positions. Now I have, if I write these equations like that, now I have three complex equations, which ends up with six scalar equations, which corresponds to six scalar equations. Now in these six scalar equations, the unknowns are W, Z, beta 2, and beta 3. Can everyone see that, please? R is given, delta 2 is given, so I know R1, R2, R3. I can calculate them. I know alpha 2, alpha 3. The unknowns are W, Z, beta 2, and beta 3. WZ is two vector equations, two complex numbers. So that means I have 4 scalars for W and Z, 2 scalars for each. I have 2 tangangles, beta 2, beta 3, 2 more. I have 6 unknown parameters. I have 6 scalar unknown parameters, 2 complex and 2 real. And I have 3 complex equations corresponding to 6 scalar equations. So I have 6 scalar equations, 6 scalar unknowns. That means I should be able to solve these set of equations. But unlike the tank-angle specification, these equations are not linear with respect to beta 2, beta 3. It is e to the power beta 2, e to the power beta 3. Can you ever see that? It is not a linear function. Although it is linear with respect to W and Z, these equations are linear in terms of W and Z, it is not linear in terms of beta 2 and beta 3. Now I have 6 equations, let me repeat, 6 scalar equations or 3 complex equations. Is 2 complex vectors and 2 scalar unknowns, 2 complex unknowns, 2 scalar unknowns, which adds up to 6. I have to solve these equations. The answer is very simple. Let me assume somehow by trial and error or some other way, I have determined beta 2 and beta 3. Somehow, somebody has given me the exact values of beta 2 and beta 3. If that is so, if I know beta 2, beta 3, these 3 equations have 2 complex unknowns. These 3 complex equations have 2 complex unknowns, W and Z. And in that case, these equations are linear in terms of W and Z. I don't know beta 2, beta 3, but let me assume that I know them. Can everyone see that, what I mean? I am assuming that I know beta 2 and beta 3. In that case, I have 3 complex equations in 3 linear complex equations in terms of 2 complex unknowns, W and Z. From linear algebra, if you have 3 equations in 2 unknowns, what can you say about that system of equation? I think you remember. What can you say? In linear algebra, if you have 3 equations, 3 equations, linear. Forget about complex numbers. If you have 3 equations in 2 unknowns, 3 linear equations in 2 unknowns, what can you say about that? What can you say about the solution?
It's solvable.
3 equations in 2 unknowns, is it solvable? Solvable?
I think so. No?
No.
But we have
If
more
you
than...
have 2 equations in 2 unknowns, 2 linear equations in 2 unknowns, if the determinant of the coefficient matrix is not equal to 0, you have a unique solution. If you have two equations in two unknowns, if the determinant is not equal to 0, you have a unique solution.
So we have infinitely many solutions in this case.
No.
No?
If you have three equations in two unknowns, in general, either these three equations are linearly related, or there are two independent equations. The third equation is dependent on the other two, or else it is inconsistent. There's no solution. Let me repeat. If you have three equations, or if you have n equations in n minus 2, in n minus 1 unknown, okay? If you have n equations in n minus 1 unknown, either if you have n equations in n unknowns, you can solve it. Otherwise, if the number of equations is more than the number of unknowns, either the coefficient of the augmented matrix must be equal to 0, or else you don't have a solution. Solution does not exist. For the solution to exist, the rank of the matrix must be equal to the number of the unknowns. The rank is the order of the determinant, which is not equal to 0. In this case, if you have three equations in two unknowns, I'm assuming beta 2, beta 3 known, I will form a matrix of the coefficients and augmented matrix R1, R2, R3. If the determinant is equal to 0, then the rank is equal to 2. Okay? The highest order of the determinant is 2. The 3 by 3 determinant will be equal to 0. Only in that case, you can have a solution. Meaning, this is the determinant of the augmented matrix. We shall be using this over and over. Please look at your linear algebra text. The determinant of the augmented matrix must be equal to 0, which means the rank of that equation, those three equations, must be equal to 2. Meaning, one of the equations is dependent on the other two. There are two independent equations. Only in that case can you solve for the unknowns, W and Z. When I write this determinant, when I expand this determinant, you see, in a way, I have eliminated W and Z. I have a simple one complex equation. This is a complex equation in terms of two scalar unknowns, beta 2 and beta 3. I have eliminated, let me repeat, W and Z using this condition. Because once I solve for beta 2, beta 3, if I solve this correctly, then these three equations must be linearly dependent. There should be only two of them can be independent. Okay? This is a very important thing in linear algebra. If you have three equations in two unknowns, if all three are independent, there's no solution. You cannot solve it. Okay? Only in this case can you have a solution. Now, you see, when I write this determinant, and I have this determinant, I expand the determinant with respect to the first column because it contains beta 2, beta 3. The term R1, R2, R3, let me repeat, R1, R2, R3, if I'm given R1 is minus R, delta 2, delta 3, alpha 2, alpha 3 are known. So I know R1, R2, R3, correct? So I know alpha 2, alpha 3. I know every term in these parentheses. What I don't know in these equations is beta 2 and beta 3. Everybody see that? I call these terms delta 1, delta 2, delta 3. Simply and expand this determinant with respect to the first column. These are the three terms that you obtain. Sorry. If you substitute delta 1, delta 2, delta 3, if you these delta 1, delta 2, delta 3, you can calculate because let me read. R is given, so R2, R3, R1, R2, R3 are known. Alpha 2, alpha 3 are known, so all these terms are known. Delta 1, delta 2, delta 3 is known. What is unknown is beta 2, beta 3. I have a complex equation in the following form. Delta 1, delta 2, delta 1 plus delta 2 e to I beta 2 plus delta 3 e to I beta 3 is equal to 0. You have seen such complex numbers in mechanisms course. If I want to solve this equation, I have one complex equation, two scalar equations. I have two unknowns, beta 2, beta 3. I should be able to solve them. In complex numbers, rather than taking the real and imaginary parts of this equation, I take this equation and its complex conjugate. In order to solve for beta 2 or beta 3, what I do is, I'm sure you have seen it in mechanisms course, I separate either beta 3 or beta 2, write the term containing beta 3 on one side, and the other terms on the other side. This is what I do. Take delta 3 e to I beta 3 on one side, and then it will be delta 3 e to I beta 3 is equal to minus delta 1 plus delta 2 e to I beta 2. And then I take the complex conjugate of this equation. In complex plane, this equation and its complex conjugate are two independent equations. Instead of writing this equation in real and imaginary parts separately, in complex plane, when you are working in complex plane, you take this equation and its complex conjugate as two independent equations. Now I have this equation, delta 3 e to minus I beta 3 is equal to minus delta 1 bar plus delta 2 bar, complex conjugate. Wherever you see I, replace it by minus I. Delta 2 e to minus I beta 2. Now, what we do is multiply these two equations side by side, which will eliminate beta 3. I'm sure you have done this in case of a 4-bar to eliminate the coupler angle. So the term is delta 3 bar, e to I beta 3 times e to minus I beta 3 is equal to e to I 0, which is equal to 1. Similarly, the other side, delta 1 bar, delta 2 bar, e to I beta 2 times e to I minus I beta 2 is e to I 0, so that can 1. Delta 2 bar, and then you have the cross terms. Delta 1 bar, e to minus I beta 2, delta 1 bar, delta 2, e to I beta 2. Now, the terms delta 1 bar, delta 2 bar, minus delta 3 bar, all these terms, if you multiply a complex number with its complex conjugate, a plus ib times a minus ib, you will end up with a squared plus b squared, which is a real term. Is that agreed? So delta 1 bar, delta 2 bar, minus delta 3 bar, you will end up with a term D, a constant term D, because all these terms are known, D. Whereas delta 1, delta 2 bar will be equal to A, a complex number. Delta 1 bar, delta 2, take the complex conjugate of A bar will be equal to delta 1, delta 2 bar. Okay? And then we let each to I beta 2 is equal to T. Each to minus I beta 2 is equal to 1 over each to I beta 2 is equal to 1 over T. Agree? So I can write this equation as AT plus A bar over T plus T is equal to 0. Since T is equal to each to I beta 2, there's no possibility for T equal to 0. So this is not infinite. In that case, I can multiply this equation with T. I will end up with, sorry, AT squared plus DT plus A bar. A and A bar are complex conjugate of each other. D is a real number. T is equal to I beta 2. The magnitude of T is equal to unity. Beta 2 is the argument of T, which is equal to, if you use A times 2, real part of T, imaginary part of T. You will end up, since this is a quadratic equation, second order equation, you will end up with 2 T values. One T value will be beta 2, the other T value, if you determine beta 2, it will be equal to alpha 2. Alpha 2 is the angular rotation of the moving body from position 1 to position 2. It is what we call trivial solution. It's the rigid body displacement. So we neglect this solution, discard it. Take the one that is different than alpha 2. That's your solution. Once you determine beta 2, you know beta 2. If you want, you can solve. Now you can solve for beta in, sorry, yes, substitute into this equation, sorry, to determine beta 3 in one of these two equations to determine beta 3, and then you can determine. So take any two of these three equations, solve for W and Z in terms of linear equations. Geometrically, consider this vector equation. Delta 1 plus delta 2 e to I beta 2 plus delta 3 e to I beta 3. This is a linear vector equation, loop equation. The loop has to be closed, a polygon. Now, forget about e to I beta 2, beta 3, it's multiplication of a vector by a complex in complex numbers by e to I beta is a rotation operator. That means consider delta 2, delta 1, delta 3. These three vectors. I don't know what they are, but they will be three vectors that I can draw for as such. When I multiply delta 2 by e to I beta 2, I will be rotating. The length is going to be the same. I will be rotating it. This tip is going to describe a circle. I don't know where that is. When I multiply delta 3 with e to I beta 3, this tip is also going to rotate. The solution is when delta 1 plus delta 2 e to I beta 2 plus delta 3 e to I beta 3 is equal to 0. That means I have two solutions. These two circles will intersect at 2 points. These two circles will intersect at these 2 points, and I will have two vector polygons. One is the one that I show in red. The other is the one that I show in blue. Okay? Now, let us consider the one in red. I will have delta 2, delta 1, delta 3. These magnitudes I know. Those are, I can determine the magnitudes of those vectors, right? I know that those vectors, so I can determine the magnitudes. Once I determine the magnitudes, delta 2, delta 1, delta 3, I have a triangle formed. Using the cosine theorem, I can determine this angle phi 2 and phi 3. And I know these vectors, so I can determine the arguments, meaning the angles formed with respect to the positive x-axis of these vectors, eta 1, eta 2, eta 3. Eta 1, eta 2, eta 3. Now, if I know these values, if I can determine these values, beta 3, geometrically, I will be able to determine like this. I'll show which one. Okay, I'll show this one. This is more complicated. Eta 1 plus phi 2 minus beta 2 is the direction opposite to this vector delta 2. Let me repeat. Eta 1 plus phi 2 minus beta 2 shows this direction. That direction is equal to eta 2 minus pi. Correct? Eta 2 minus pi is equal to eta 1 plus phi 2 minus beta 2. From which beta 2 is equal to eta 1 plus pi plus phi 2 minus eta 2. I can determine beta 2. Apply cosine theorem over here and determine the angles for each of these vectors. Beta 3, similarly, is equal to eta 1 plus pi minus phi 3 minus eta 3. Okay. If I draw it like this angle is eta 1. First eta 1 plus pi minus phi 3 minus beta 3 is equal to eta 3. This is this equation. Take eta 3 to the other side. This is this equation. Okay? So, if you do the inverse in a similar fashion, you will end up with these two equations. Okay. Circle point specification. I think I have time for this as well. Circle point specification. If I'm given minus z, again I have to rewrite these equations taking z on the right side. I can write them w plus r minus equal to minus z is equal to z1. W e to I beta 2 plus r is equal to delta 2 minus z e to I alpha 2 is equal to z2. W e to I beta 3 plus r is equal to delta 3 minus z e to I alpha 3 is equal to z3. Again, I have three complex equations in 6 scalar unknowns, 2 complex unknowns and 2 scalar unknowns, beta 2, beta 3, w and r. In a similar fashion, I say, okay, if I know beta 2, beta 3, these two equations will be linear in terms of w and r. So in order to have a solution, the determinant of the augmented matrix must be equal to 0. This matrix must be equal to 0. This time I know Z1, Z2, Z3. I know delta 2, alpha 2, delta 3, alpha 3. I have this complex equation. Can you see that? Again, if I expand it, I end up with a very similar equations as before. And the solution is the same. Or, let me say this, invert the motion. We have seen if circle points is center point, if you have a solution for a center point, you can always convert it to circle point equation by simply inverting the motion. This is your original motion. I have a fixed frame. I have a moving frame from position 1 to position J. If I keep the moving frame in the first position, release the fixed frame in red, but while keeping the relative positions, these two relative positions the same, all I have to do is bring back this coordinate system, the origin, to the first position, but minus delta J, but that is not going to give me the angular position, and I have to rotate it by minus alpha J. Delta J e to minus delta J e to minus I alpha J. And the angular rotation of the fixed frame relative to the moving frame will be minus alpha J. So original motion, if original motion is delta J, alpha J, the inverse motion will be delta prime J, alpha prime J. Delta prime J will be equal to delta J e to minus I alpha J, and alpha J will be equal to minus alpha J. Alpha prime J will be equal to minus alpha J. All you have to do is invert the motion. In that case, whenever you invert the motion, what was the center point becomes the circle point. Okay? And use the same set. Okay. Now, we have this dyad formulation. We have three different possibilities. One is basic form. You are given the three positions, and you assume beta 2, beta 3, determine W as C, from which you determine circle point and center point. That is Frank angle specification. Center point specification is given R, which is equal to minus R1. Solve for beta 2, beta 3 using compatibility condition. And then solve for circle point minus Z from any two of the equations. Circle point specification, given minus Z, solve for beta 2, beta 3 using the compatibility condition. Then solve for the center point R from any two of the equations. Or invert the motion, solve problem 2, given R. Okay, when you invert the motion, minus Z will be R. Okay, that's it. Let me repeat, you can solve those equations in MATLAB, MathCAD, whatever you want to you can use. But in this course, we have function routines in Excel. It is very simple. These function routines are very simple, you know, at most 20 lines, very simple. For For example, function 3 position basic, alpha 2, alpha 3, delta 2, delta 3, beta 2, beta 3. You have to give the 3 positions by these alpha 2, alpha 3, delta 2, delta 3. Delta 2, delta 3 has to have 2 terms. It's a vector. Beta 2, beta 3, and alpha 2, alpha 3 are scalars. These are expansion of those multiplications, delta 2 times e to the beta 2, etc. And then, as a result, you determine W and Z values. Okay? 3 position basic. This, you have to mark 4 cells in a row, and you will get the result. I'll show you in a minute. There are several different functions that you can use. Function 3 position basic, let me repeat, this returns both W and Z. 3 position basic 2, instead of returning W and Z values, it returns minus D and R vectors. Sorry, because the reason is you want to minus D and R is the location of the circle point and center point. Minus Z is the location of the circle point with respect to the first position. And R is the location of the center point with respect to the first position. So it's more useful, I would say. Function 3 position fixed pivot. In this case, you again define the 3 positions, alpha 2, alpha 3, delta 2, delta 3, and R. R is the location of the center point. It will return this function, 3 position fixed pivot, will return beta 2, beta 3 values for given 3 positions. Function 3 position 2 fixed pivot, here's the 2, alpha 3, alpha 2, alpha 3, delta 2, delta 3, and R. Again, it has the same arguments as fixed pivot, but this time this function returns minus Z vector. Okay? You don't need beta 2, beta 3. You are given the center point, determine the circle point. That's it. And this function 3 position 3 moving pivot, given alpha 2, alpha 3, delta 2, delta 3, ZP is minus D. This function returns the center point location, fixed pivot location, minus Z. ZP is minus Z. Moving pivot location is specified. Let me show in class. Okay. Here I have 3 positions. I have already defined the 3 positions as such, okay? And I have plotted them. First, let me show you these functions. Maybe I should do it like this because of that thing over there. Go to the developer menu, Visual Basic. By the way, if you have downloaded this 3 position bus file, please reload it because I have corrected, revised it, added some new functions. That's the only thing. Reload it again. Basic function, you already know, solution of simple mechanisms. 3 position function. Here you will see 3 position basic, alpha 2, alpha 3, delta 2, delta 3, beta 2, beta 3. And you obtain W and Z. 3 position fixed pivot beta. You have the beta 2 and beta 3 values are given, are obtained, fixed pivots. Forget about these. You can check what those perform. 3 positions, 2 fixed pivot are, it returns minus z vector. 3 position moving pivot, zp is given, the returns r vector. 3 position basic 2 returns minus z and r vector. 3 position slider, I'll discuss them later. Okay. These are the functions. Let us see how we can use it. I have taken considered a few things. Crank angle specification. Let us see that first. I have these three positions are given. I have determined delta 2, delta 3, alpha 2, alpha 3, as you see, 30 degrees, 60 degrees, 4, 0, 12, 0. I mark 4 cells like this. I'm going to obtain W and Z. Formulas, function routines, user-defined, it starts with T. As you can see, I have so many T's. Consider 3 position basic. Returns W and Z vectors, Wx, Wy, Zx, Zy. You must enter the 3 positions of the moving body, delta 2, delta 3, alpha 2, alpha 3, and the crank angles, beta 2, beta 3. I think that's obvious, right? I mean, that's what is specified. Click OK. You have to enter those values. Keep in mind, angles must be in radians. Okay? Alpha 2, alpha 3, delta 2 is a complex number. Delta 3 is a complex number. Beta 2, here I have. Beta 3. That's it. You can see the result. I'm going to obtain 4 numbers. Control Shift, Enter. W and Z. Okay? If you want, starting from mine, I think I have done it over here, but I'll do it now. If I want to determine.
Hocam,
Yes, sir.
while we were choosing beta angles, we chose the degrees, not radians.
Oh. That's a big mistake. Thank you. I'll correct it. Control Shift Enter. Okay? Have I corrected it? Thank you very much.
Thank you, hocam.
Okay. Yes. A will be equal to minus Z minus Z. A0 will be equal to A minus W. So that vector will be okay. Now, A0 is 6, 3, so this is A0. That's fixed. This is A. No fill. Dotted line. Oh, okay. If you want, add data labels. I wanted to show this. A0, subscript. This is going to be A1. Let's make it bold. And then subscript. Okay, that's one query. Notice I have obtained A0 and A from W and Z vectors. W is from A0 to A1. Z is from A1 to the origin of the coordinate system over here. Now, let me use another vector to obtain minus Z and R. Formulas, user-defined, 3-position basic 2. Again, I have the same input, alpha 2, alpha 3, delta 2, delta 3. This time I won't make that mistake. Beta 2, beta 3. Correct? Now, Control, Shift, Enter. Please check my A0. A0 is 6.5697 plus 3.966 I, X and Y coordinates. Is that correct? Can everyone see that? You obtain the same result. Now, instead of using angle specification, let us use circle point specification. 3.7, 4.8. 3.7, 4.8 is somewhere over here, okay? Formulas, again go down to 3. 3-position circle point, moving pivot. Returns the location of the fixed pivot R when the 3 positions, alpha 2, alpha 3, delta 2, delta 3, and the location of the moving pivot minus Z is specified. R, Z, delta are 2-dimensional arrays. Is that agreed? Click OK. Again, it asks for alpha 2, alpha 3, delta 2, delta 3. Zp is minus z. It is this value. It is the location of the moving pivot, circle point. Okay? Control Shift, Enter. You have marked 2 cells because it's going to return R only. Okay? Let me draw that line again. Select data, add. Is that okay? I'm not going to do all that thing because I don't have time. Center point. Okay. Again, mark 2 cells. Formulas. Three position, fixed pivots. If you use beta, it will return angles. No, I don't want that. Fixed pivot. Let's see that. Returns the location of the moving pivot minus z, minus zx minus zy. When the 3 positions, alpha 2, alpha 3, delta 2, delta 3, and the location of the fixed pivot R is specified. I think that's very clear. Is that agree? So, alpha 2, alpha 3, delta 2, delta 3, R. That's it. Control Shift, Enter. Let me show that as well. Any questions, please? You have to select 2 of those. By the way, what you can do is, I'll show that as well. Which one? Okay, I'll take beta 2, beta 3. Once you've done this, usually you will need some trial and error, as you know, because some of the mechanisms, some of the solutions will not pass. It will not be feasible. You will not be able to obtain you see, these 3 positions, the mechanism with these link lengths will exist at these 3 positions. Whether it passes through these 3 positions is another problem because there is a branch problem. One of the positions may be on the other branch of the 4-bar. You see, a 4-bar has 2 branches, which we call open and cross form. You don't know in which branch these positions will be. What you want is all these 3 positions must be in one branch of the 4-bar. If it is on the 2 different branches, that 4-bar cannot exist, cannot be, you cannot use that. So you have to check that first. And then you have to check the transmission angle. And then you have to check whether, you know, there's an obstacle. Or then you have to check whether you can design it or not, or lots of things. But basically the procedure is you have to use this formulation and then check your results, see that all your other conditions are satisfied. That's engineering. That's the design process. Okay? So what I can do now is, that is the beauty in using computer programs in these cases. Okay. Developer, insert. I will insert and then Control C, Control V. I'll have two of those. Just to show you what you can do with these. You can do it for circle point specification, center point specification, the same way. Usually this is what I like. These are the spin buttons. This point is D11. Properties. I have to link this cell to D11, correct? Okay, I'll change it from 0 to 100. And then step up 1, okay, correct. And then I'll relate this to D12, 0 to 100. Okay, since this is 25, okay, like to do it like this. As you can see, I can change these numbers. So what I will do is equal to minus 20 minus this value, or minus 15 minus that value, minus 10 minus that value. That is 120 is equal to minus 100 minus this value. Of course, you can change the range which you are going to do this search. So this is simply what, this is what I have done. You can change that range. You can increase it or decrease it. As you can see, I'm obtaining different solutions. Is that agree? You can do the same thing for these values as well, okay? So you can very easily trace different solutions. Any questions, please? Okay, I'll post this file, save as. In class, let me write it so that you can see the difference between those two. Okay? Let me say one thing for sure. Please go to the Visual Basic and try to understand what the hell is being done using these functions. Otherwise, you will not be able to use it. It's an open source. So you know what the hell each one of them is doing from top to bottom. Okay, you know each one of these functions. Okay, what you should do is, you see, besides you're learning how to use those functions. You should know how to write those functions. The thing is, as an engineer, in today, we are not performing our engineering computations using a calculator, as you usually do in your courses. We are solving our problems using computer. Whenever you are using a computer, you have to use certain tools, either made by other people or you make your own tools. You have to know how to make these tools. You have to know how to prepare these tools, okay? That's why I'm telling you to learn what the hell is going on, how to write these function routines. Whenever, you see, in my case, whenever I see that I have to repetitively perform some kind of a calculation, I write a simple function. It makes my life easier, okay? Whenever you see, I don't have to solve for a 4-bar over and over. I have a 4-bar function that I can solve right away. I have a 3-position basic function that I can solve a 3-position problem. Later you will see I have another simple function to solve for 4 positions and to solve for 5 positions. Okay, the idea is you have to know how to write these functions. Okay, let me repeat, all attendance is being recorded. Tell your friends, and I'm going to be very severe. I mean, please note this. You cannot pass this course without attending it. I'm very serious about that. If necessary, I will stop recording. I will not record the course. I'm very serious. Okay, I think I'll stop sharing. And I'll stop recording.